Good evening, sir. This is K.haimavarshini. I am from CSCB section. My roll number is 244g1a05b3. Today's my topic: Schrodinger's time-dependent wave equation. Introduction to Schrodinger's wave equation. Schrodinger's wave equation is a fundamental equation in quantum mechanics. It describes how the quantum state of a physical system changes over time. The time-independent version focus on states and potential energy. Historical context. The equation was formulated by Eugene Schrödinger in 1926. It marked a significant shift from classical mechanics to quantum mechanics. Schrödinger's work was inspired by the wave practical uses of matter. The equation formulation. The time-independent wave equation is written as here it is. Signification of the wave function. The wave function provides production of finding a practical in a given state. The square of the wave function's absolute value gives the probability density. Understanding the wave function is critical from understanding the behavior of quantum system. Boundary conditions and solutions. Solutions to the time-independent wave equation dependent on the boundary condition. Common boundary conditions include infinite potential walls and harmonical oscillator. These conditions lead to continued energy levels including the nature of quantum systems. Example: practical linear blocks. The practical linear blocks is a classic problem in quantum mechanics. The potential is zero inside the box and infinite outside, leading to discrete energy levels. The wave functions for the system are significant and must satisfy boundary conditions as well as the walls. Quantum tunneling. Schrödinger's equation explains the phenomenon of quantum tunneling. Tunneling occurs when practical potential boundaries, even classical, fall behind ones. The concept has implementation in electrical foundation and semiconductor. Boundary conditions and solutions. Solutions to the time-independent wave equation dependent on boundary conditions. Common boundary conditions including infinite potential walls and harmonic oscillators. These conditions lead to quantum energy levels in expression the nature of quantum systems. Quantum tunneling. Schrödinger's equation explains the phenomenon of quantum tunneling. Tunneling occurs when practical potential boundaries, even classical, fall behind ones. This concept has inspired in These concepts has inspiring in neutral positions and semiconductor physics. Comparison with classical missions. In classical missions, practicals have defined positions and voltmeters. Quantum missions through the Schrödinger's equation introduce voltmeters and physical behavior. These fundamental differences highlight the limitations of classical descriptions from microscope systems. Applications in physics and chemistry. Schrödinger's time-independent wave equation is widely used in atomic and molecular physics. It aids in depending electronic configuration and chemical boundary. The equation also plays a circular role in developing technologies like quantum computing. Conclusion. Schrödinger's time-independent wave equation remains a constant of quantum mechanics. It provides deep insights into the nature of matter at microscope scales. Continued research in this area expands our understanding of universe and its fundamental laws. Feel free to observe any of the concept or structure as needed. Thank you, sir.